whenever you're ready. No problem. Yeah. Okay.
All right, it's 8:30, so let's get started. So I'm very pleased to have Allison and her colleague Heidi from the library. They're going to give us a talk on machine learning. So if you guys saw the link I emailed you guys yesterday, this is shaping up to be a game-changing general-purpose technology for the next several decades. Okay? And what that means for us as business managers is, we, especially in finance, we should be comfortable with the tools and techniques that are here. Okay? Now, we don't cover some of those things in our class, so I thought it's really good to have someone like Allison come and give a talk here in class. She's an expert on this, and you'll see you can go ahead and use this kind of technology in a wide variety of scenarios. And I just checked with them. They are extremely willing to help us out. So in case you have any questions even later on, I'm going to take the liberty of saying they're free for your free resource for us. Okay? Very different from what's there in the computing center. Okay? So in case you don't know, our library actually is taking the lead in data visualization. So that's something that we may or may not know, but I think it's very good for us. Now, I'm done. I'm going to go ahead and take up my spot all the way to the back. The next 75 minutes is all yours.
Thank you.
Thank you so much,
Right.
Allison. Thank you.
Thanks, everybody, for having us. Again, I'm Allison. I'm a data and visualization librarian over at DHL Library primarily. And Heidi Tebbe, my colleague, is a collections and research librarian for data science and engineering. So if you ever have any questions regarding cleaning your data, making graphs and charts, and we're going to be using R today, which is a statistical software. Kind of like, has anyone used SAS before? Do you use SAS here? Yeah, so it's kind of an alternative to SAS. It's free and open source. We do consultations on R and SAS. Please feel free to look us up if you have any questions, and I'll share my contact information with you guys as well later. We're going to get started today. I'm going to do a brief lecture about machine learning and provide kind of a gentle overview and some of the main topics to be aware of. We're also going to do a hands-on activity with R, and I want to kind of start with that because the very first part of that is to install some packages, and it takes a little while to install them. So I want to have everybody doing that and having the packages installing during the time that I'm talking. So then when I'm done talking, we'll have time for the hands-on activity. In order to do that first, you'll need to have downloaded all the class files for today's workshop. And those are, again, located here at this Go link. So if you haven't had a chance to do that already, the easiest way to download all the files is to go to the Go link and then click on that arrow for the folder name and then go to the download link and download it all at once. And it will download it as a zipped directory. And then once you've downloaded it all, you'll go to your computer, find the file on your computer and kind of unzip it. So depending on whether you have a Mac or PC, the unzipping process is a little bit different. So if you have any questions at all, like how to do any of this stuff as we're going through, Heidi's back here to help. So if you'll just raise your hand, she can come around and help you if you have any troubles. So if you have a chance to go ahead and do that, great. Once you've downloaded the file, go ahead and open up RStudio. And when you open up RStudio, it should look a bit something like this. You're going to see more than likely these three windows. The window on the bottom right has a number of tabs, but the most important tab that we're going to start with is your Files tab. So the Files tab is actually just showing you all of the files on your computer. And you're going to probably be starting in your home directory. So if you kind of scroll through those, you'll see that these are actually just the files on your computer. What you want to do is find the folder for the class files called ML participant files. You want to find where that is on your computer here inside of this file tree. So you want to click into the folder where it's located. I have mine located in my documents directory. and you might have yours in your downloads or your desktop, wherever, but go ahead and try to find that. The easiest way to find where it's located, rather than having to like scroll a lot and click a lot, is to actually click on this little button here. It's kind of not showing it. Let me move this over. This little button, it's like this little 3 dots. It's far on the right over here. If you click on that, it will bring up a browser window so you can find the file much easier that way. So go ahead and do that. And once you find the file, click into it, and you should see this list of files here. You'll see some data sets. You'll see helloworld.r, linear.r. Once you're inside of that, that's where you want to be. And when you get inside of that, and I'm going to leave this up here for those of you who are still looking for your folder, you want to click on this little blue gear, this more, where it says more, and it's going to bring up a drop-down menu, and you're going to select Set as Working Directory. And what this does is it sets the project directory for where we're going to do our work, and it makes it a lot easier to find the files we need to once we get inside of once we start actually writing code. So once you've done that, what you'll do is you'll click on Set as Working Directory, and you should see in your console, it should pop up with this blue line of code that basically tells you that the working directory has been set. So, yep.
So in my RStudio, I have actually 4.
Yes, that's fine. Yeah, you might have 4 screens, and we will have 4 screens. If you've clicked on any of the R files, like if you click on linear.r, it will bring up that script inside of a 4th window. So that's fine. So take another minute or 2 to make sure everybody's got this part, because this is kind of the most important part of the whole thing, to make sure you have your working directory set. That is you need to, I also need to download it.
Yeah. No. Sit there.
So in your browser window, just go ahead and type that link. The purple on the board here, go. Solid issues or help with finding files or anything else? Okay. Give it 1 more minute. Talk a little bit about what R is briefly. So R was created by a couple of professors in New Zealand in the 1990s because they wanted their students to be able to use statistical software that was free. We're really lucky here in the state because we have access to SAS and all this stuff. But at the time when they were creating, when they were teaching statistics, the students, they wanted them to have access to free software. So they created R, and they never knew that it was going to become as big as it is now. It's one of the most popular languages for statistical computing and for data science. More than that, you can do web scraping. You can get data from APIs. You can do a lot of stuff with R. You can do text analysis, text processing, text mining. So we're just going to kind of just like touch the tip of the iceberg today. We're going to do a little linear regression with R, but just kind of so you have the background of where it's coming from. Okay. So as long as you've got your working directory set, now we're going to open up linear.r. And when you click on linear.r from your files link there, you should see it pop up in a new window there on the top left. This is the script we're going to be working with today. And we're just going to focus on the first section right now. Step 1, we've already done, setting our working directory. Step 2, we're going to have to install some packages. So R has like a base package, which you downloaded already, but there's all these other packages that are basically programs that you can bring in to R to do other things. So it gives you access to lots of different functions that you might need for data analysis. So in this case, we're going to install some packages for graphing, ggplot2. We're going to install a reader package, which is for bringing in CSV files and other data. Caret is for machine learning. Metrics is some more machine learning related stuff. And then dplyr is for data manipulation, when you want to filter data, subset it, that kind of thing. So all we have to do is highlight these lines. So we're going to highlight the green, the stuff in green with the pound in front of it. Those are just comments that I've made for you to be helpful. So everything in green, the computer is going to ignore. So you want to highlight lines 11 through 14 and just click Run. The Run button is in your panel, your top left panel here, right above the script. So if you click Run, it's going to start installing the packages for you. You only need to install the packages once until you upgrade your R version. So if you've already used R and you've already have these packages, obviously you don't need to redo it. I've already installed all these packages, so I'm not going to redo this because it takes a while. But when you're installing them, you should see a lot of text appear in your console, and often it's red. And that's generally okay, unless you see the word error. But don't be alarmed if you see a lot of kind of red text scrolling, okay? So that's normal. And once it's finished, you're going to see, again, this little blue prompt like you see here. And that's basically saying it's all done. But it's going to take a while. Okay. So if you see any errors, just let us know by kind of raising your hand, and Heidi will come around and help. Does anybody need another minute to get to this point of clicking Run? Okay. So I'll go ahead and give you guys a brief overview of machine learning and kind of why it would matter for people in business and finance. The main goals are just to kind of give you kind of a basic understanding and what the processes are in terms of if you wanted to actually do some machine learning yourself on data, and how you would do that, how you would train a model and how you could test it, and give you a little bit of hands-on experience with that. Using something that's pretty familiar. We're going to be just doing linear regression, which using mathematics that you've learned in middle school and high school that you've worked with before. So it's not going to be super hard, but the process is very similar. It's all you have to do is kind of switch out the algorithm. We're going to be using a simple algorithm, but you can switch that out and use the same process to do other types of machine learning. So that's kind of the goal we're going to work with today. How many people have been following stock market recent kind of ups and downs, extreme swings? Yeah. And you guys have probably done a lot more reading and talking about this. But in the first week of February, we saw there were a couple of days when the stock market fell by over like 1,000 points, right? Dow Jones Industrial Average fell by over 1,000 points. And then there was another day in which it went up by over 500. So what was interesting about that, right, was that these downs and ups and downs are such extremes. And so reading a bit about why that's happening, again, volatility is caused by lots of factors, but the extremes of those ups and downs have been attributed to, by some analysts, to algorithmic trading or automated trading, right? The idea that there's computer code out there that's handling buying investment decisions, that is, computer programs are buying and selling stocks in an automated fashion, which for some reason has kind of attributed or created these highs and lows that we're seeing, right? And so it's interesting, right? Because algorithms, which are basically just sets of rules that computers follow, right? The algorithms could kind of be behind all of this stuff. And these are machine learning algorithms. And so machine learning is really useful because using computers, we can do things a lot faster and more efficiently than we could. Computers can handle calculations that our brains can't much more quickly. But they also don't have the human intuition, right, that humans have. And so it's interesting to see what happens when you let algorithms just do their thing, especially in markets. So just to say that machine learning is a really hot topic right now. It has been for the past few years. Last year, JP Morgan put out a 280-page report on machine learning and artificial intelligence, which is a subset of machine learning that we'll talk about a little bit more in a moment. But just kind of a guide for investors and how they might incorporate more machine learning into their investing strategies. So we're seeing more and more kind of reports and presentations. And in that report, the authors, who are data scientists at JP Morgan, said the exponential increase of the amount and the types of data available to investors have prompted some to completely change their investing strategy, their business strategy, while many are still paralyzed in the face of what is also called the fourth industrial revolution. So this idea that large amounts of data have created this industrial revolution almost that we're living in now basically means that data is this really, really important resource that's changing technology and changing the economy. And people have described data as like the new oil in a way, so that the companies that are able to harness massive amounts of data and analyze them are going to be able to get like leading edges over their competitors. So because it's a hot topic, you might see now these online courses popping up related to machine learning and finance or machine learning and trading. And so here's one that Georgia Tech has created that's offered for free on udacity.com. There's a lot of these now. You might see these online master's degrees popping up about data science and business and all of that. And that's just a symptom or kind of an indicator that the topic has become super, super important. So what is machine learning? This is a kind of the most general definition here that you'll see, and this is a really early definition coming from 1959. But the idea that you can train computers to do something that they haven't been explicitly programmed to do kind of doesn't make a lot of sense. But the idea that you can give a computer a set of basic rules and then they can go on from there and essentially learn. So an example of this would be like a self-driving car, right? You guys know, as you know, when you're driving, or if you've been in a car, right? There's no way to make a list of all the possibilities that can happen to you while you're driving, all the different scenarios, right? There could be something that runs in front of the car. There could be a child. There could be an animal. There could be a leaf that blows in front of the car while you're turning, while you're, so all these, there's really an infinite number of possibilities, scenarios that could happen. There's no way a person could write a program for a computer to be able to handle all of those scenarios, right? So how do self-driving cars work? Because you can't write a program to tell a computer, the car's computer, you can't say, well, if this happens, then do this. If this happens, then do this. It's just impossible. So these cars are outfitted with all these different sensors, and the computers that are in that car, right, are given a set of rules to follow. But they essentially have to take in information, right? The computer code takes in information and has to essentially learn from that and make decisions based on that. And so it's actually, the thing about that is, like, we don't fully know how some of these things work. We don't fully know how some of these machine learning processes work. So to break it down a little bit more here, so we're teaching a machine how to perform tasks. We're also teaching machines how to identify trends in data and patterns in data that we can't do ourselves, and make predictions on data. So it's like, what can a computer find that there's just so much data that we couldn't find ourselves, and how can we use that to our advantage? It's supposed to be like something that helps humans, right? The whole purpose is to help us. But as we're finding, as computers get more and more intelligent, and we get more into these complex algorithms that, like in this example, this is an article that was recently published in the MIT Technology Review, that we're seeing some of the algorithms are so complex that computers are taking on kind of minds of their own. And we can't really explain the outcome of what's happening. And this is related to a new self-driving car that was just released. But it's kind of interesting to see what's going on with technology. When you encounter machine learning, you might encounter it online. We're seeing more and more chatbot type programs. So they're robots, but obviously they don't have physical embodiment. They're not like physical robots rolling around, but they're on the computer. So we're seeing artificial intelligence used in, for example, helping people as personal shoppers, helping people make decisions about what to buy based on certain characteristics they provide. And they can interpret natural language and talk back to you. Has anybody ever chatted with an online bot? Or, yeah, I've recently gotten a phone call from an AI bot, and the person sounded like, the bot sounded like a real person. The only thing that was different was it was like, there were all these kind of awkward pauses that you could tell, okay, this isn't actually a person, this is a robot. So in this new kind of, we could call it industrial revolution, one thing that we're noticing with artificial intelligence is that it is replacing human labor in certain fields. So a robot would replace, in this case, a personal shopper. And here's a little video I wanted to play for you real quick. Let me make sure I have the sound plugged in.
You've made some money. You want to invest, and you're wondering how to get started. Traditional financial advisors have high fees, high account minimums, and try to sell you products that benefit them, not you. But at Wealthfront, we know there's a better way to do it. We've taken the same modern portfolio theory that drives some of the most advanced financial advice. We're making it available to you. We use risk assessment algorithms to define the level of risk you are comfortable with, and from there, build highly individualized plans. We show you your plan so you can see what you'll own before you commit. Then just fund your account, and we'll open an SIPC insured brokerage account for you. You can even transfer your IRA or 401k to invest in your plan. We continuously monitor your portfolio and periodically rebalance your account to keep your plan on track. The dashboard shows you everything you want to know about your investments. And what's more, you pay 75% lower fees than typical financial advisors. Wealthfront, the financial advisor for the new generation.
So you notice they're really trying to appeal to younger investors, right, for the new generation here. And this is very interesting because essentially what it is robo-advising, right? It's algorithms, machine learning algorithms that are taking information about a person and helping them make these investment decisions. Again, replacing the investor, right? The financial advisor that's going to help you, right? Let me not play that video again. So just a quick breakdown of the types of machine learning tasks that are out there. Generally, they fall into these 4 categories. One would be classification. 2 is clustering. And I'm going to go through some examples of these in slides. Regression, association, rule discovery, and anomaly detection. So we're trying to use these to help us do things like find patterns in data, find classifications in data, and also to help organize how we, well, in a business situation, how we put our products out for people to buy, like location of our products, for example. Classification algorithms, this is kind of a basic example of like teaching a computer to identify images and determine kind of what it's looking at. So we might train a computer to look at various pictures of dogs and cats, giving it some historical data of like dogs and cats photos that are already out there, and then give it a new image and get it to statistically determine whether it's looking at a dog or a cat. And so if you get it something like this, then it might like probably would say this 50% likelihood of being a dog, 50% likelihood of being a cat. So it's going to give a statistical probability. So like if you give it a dog photo, it might say 70% it's probably a dog, 30% it's probably a cat. Okay, it's a dog. So that's the kind of the output that you would get. You would get a statistical output, right? You get a numeric output, and it would say dog or cat. In a clustering algorithm, you're giving it some data points and trying to figure out if there are any groups in the data. So this is some data points about flowers and their height and their petal width. And how many clusters do you guys see in this data? 4? 3? Yeah. So it's kind of one of those things where it's like, okay, here's a couple of obvious ones, and then what's going on here? And so depending on how the algorithm has been trained, it might return 3, it might return 4, and it kind of depends on how you've trained it, right? So training an algorithm, there's a lot of like tweaking going on, and also in human work that goes into that as well. And so using a certain algorithm called k-means, it's found 3 clusters, right? And it's like, well, this kind of looks like 2 separate clusters, but the computer sees them as one. Then, of course, there are these regression algorithms which try to look for the relationships between variables, 2 variables, or 2 or more variables, right, to see if there's any kind of pattern. We use that a lot in predicting. Today, we're going to look at whether salaries affect how happy an employee is. So we're just going to come up with a prediction algorithm to see if we pay this person this much, are they going to be happy? Are they going to be this much happier, right? Which is a simple example, but that's the kind of idea. Then we have association rule mining, which is finding patterns between kind of things that you might not realize. Has anybody ever heard that there's a study about how purchases of diapers and purchases of beer are somehow correlated? Have you ever heard that? So that there's a study about this and how it seemed like there's some connection between purchases of diapers and beer, and it traced it back to basically dads going out on Friday nights and buying diapers and also buying beer. So and I'm oversimplifying the study, but the purpose of that was to say, okay, grocery stores, you should put the diaper aisle and the beer aisle really close to each other. So if you go to a grocery store, you can kind of see, okay, how are things located in proximity to each other? And in this example, it might be that you put the milk and the bread really close to each other because people tend to buy those things at the same time. So that's the kind of thing that you're looking for in doing that kind of machine learning activity. And then there's deviation detection, and you see this a lot with like credit card fraud detection, insurance fraud. Often it's trying to find people committing fraud and stuff like that. But basically, just trying to find these outliers in the data. And the outliers are, in this case, in a situation of credit card fraud, would be like, well, somebody's used your credit card in a completely different country or a completely different part of the country. And that's kind of a red flag that maybe there's some fraud happening on your account. All right, so I'm going to talk briefly about what the processes are when we do machine learning. And so then we're going to kind of go through this with an activity in a couple minutes. The first thing is to get the data, right? And the data can come in a lot of different forms. It could be image data. It could be data from files. You could be getting data from Excel files or from a database. You could be getting it from a web API or like from a web portal or web scraping or something like that. And then you're going to put it into some kind of software. You might use SAS, you might use R, you could use Python, some kind of software where you're going to be generally using code to deal with it. There's more stuff that's coming out. I know SAS has some products now where you don't actually have to use code to do some of these techniques. Software is often very expensive because it took a lot of work to create it. But if you know how to code, if you know R, you know Python, you know these kinds of open source tools, then your job's a lot easier and cheaper. So once you get the data, you often have to clean it, and this is what takes the most time. It's just getting your data in the right structure for analysis. And not just machine learning, but when you're like creating charts and graphs from your data, even if your data's in Excel, or you're using Tableau or some kind of software that you can make charts with. Sometimes your data comes in this really, what I would call like a messy format. And it doesn't really look messy, it's very kind of neat. But what the ideal structure for data is that you would have one variable per column and one observation per row. And so if you notice in this particular example, you have like people's names. So, okay, name would be the column header we would need for this. And that would be one variable, person's name. And then we have treatment A and treatment B. And arguably, treatment is really one variable and should be one column. And then you can have the treatment types listed as the values in that column. And then the result of the treatment is going to be its own column. And that's the result is its own variable. And when you have data structured like this, it is so much easier to deal with. It's so much easier to create your graphs from. And if you ever have any need for doing this kind of data wrangling, data cleaning, give us a call or send us an email or something at the libraries, and we can meet with you and work with you to do that if you need help. Also checking data quality, just making sure like there aren't any weird issues or symbols that are throwing off the software. Everything is spelled correctly and uniformly. There aren't any random weird spellings of the same thing. That's always kind of like, that's an obvious point. But then when you're doing machine learning, you have to also look at the different variables in your data and figure out which ones are more important than others for training your model. And so this is data from the Titanic. So the Titanic sank, this big ship that sank, and not everybody survived. A lot of people died. But there's a data set that's kind of famous out there now. It's free. It's available to the public, of listing the people, their names, what their titles were, how old they were, the family size, and you have all these different variables about these individuals. And this is an example of what variables determined whether they lived or died. What variables in the data were most important? Turns out the title was the most important, meaning Mr. or Mrs., Miss, the most important indicator of whether the person lived or died, right? So between a Mr. and a Mrs., who's more likely to survive? Mrs., right? So women were put on lifeboats before men. And also how much they paid. That's more of an indicator of maybe their wealth or their class status, right? And so you often have to do data analysis to figure out, and this is part of the machine learning process, is figuring out what variables are most important to use in your model. So because of that, in this case, in that same data set, we have a person's name, first and last, and we also have their title, and it's all in one column of the data. But because the title was the most important for determining whether they lived or died, we're going to need to break this out. In our data cleaning process, we're probably going to break this out to have a separate column for title, where we actually have what their title was, and that would make things easier. It's kind of like hindsight is 2020, since we already know it's an important variable. But again, like, that's the kind of example of data cleaning that you might have to do. Even though the data looks clean, it's not super clean yet, because you need to kind of create more columns for important variables. So once you have the data all prepared, then the next step is to train a model. So it's like, I keep saying this word model, and what does that mean? A model has two parts to it. The first part of the model is the data itself. So it has the data that's already prepared. Second part of it is the algorithm that you're using. And so here's just a few examples of different kinds of machine learning algorithms that could be used. We're going to be looking at the linear regression one, but there's also the one we've looked at that does clustering. There's also the one that the algorithms that are used in self-driving cars and the artificial intelligence bots. They're neural networks, which really try to mimic how like the brain works in a way, and they get very, very complicated. Decision trees, so trying to figure out, based on a set of like yes or no answers, something, should you do this or should you do that, right? And it goes through a kind of list of questions and it spits out an answer, right? So that's a simple example of a decision tree algorithm. Random forests are useful if there's lots of variables that are going into something and you don't really know which ones are most important. It's an interesting algorithm because it's useful for classification and regression. So it's when you have lots of variables and you're not really sure their relationship, people often will start off with random forest algorithms. So the process is often like starting with something, realize it isn't working, and trying something else. It's one of those kind of like, it's like an art rather than a science in some ways, right? Okay, art and science. So this is just kind of a visual of what a model is, the training data and the algorithm. The data that you give it is historical data. It's data that's already happened, and that could be patient data in a drug trial. It could be a person's or Amazon.com purchase history. It could be like billions of rows of data, terabytes of data. It could be more data than that. Stock market data over time, financial records, audio records. So any of these kinds of, and many more kinds of data have been used in machine learning projects. And the purpose of giving something a model historical data is to then eventually be able to give it new data and have learned from the old data to make some predictions or do something with the new data. And so in this case, in this simple example, we have a bunch of dots. Some are brownish and some are blue. And we're going to train the model and say, okay, these are the brown dots and here are their characteristics. They're brown. They also have other qualities, imagining. And then here are the blue dots. And so now we're going to give it this new dot, and we're going to say, okay, model, tell us whether this dot is going to be brown or blue, right? And so it looks at the characteristics, and then it gives us some kind of answer. And the training set is really important. The training set is like a random sample of the data, the original data. So you don't necessarily use all the data for training. You have to divide it up and use some of the original data for training and some of it for testing. And so that's actually what we're going to be doing today. We're going to have a data set that we're going to divide up and train our model, and then we're going to test our model. And I've already talked a little bit about the testing process. And to do testing accurately, you have to use some statistical functions for that. And the interpretation process can be a little bit challenging, and there's different ways of testing depending on the algorithms that you're using. And so, of course, the last process is just to figure out if it was effective. Look at the training data. Did your model do a good job of what you wanted it to do? And then improve it. There's a lot. It's kind of the cyclical process of just testing, improving, and testing some more. So that was a very quick kind of overview of the basics of machine learning, and I wanted to give us some time to actually do our hands-on activities. So hopefully, if we go back to RStudio, hopefully your packages have all installed properly, and if not, that's okay. We'll be able to deal with it as we go along. So the first exercise we're going to do is to try to predict whether somebody's happiness and salary are correlated, right? Their job satisfaction and their salary. It's kind of it's a little bit of an artificial exercise, because it's well, we've got to take into account there's other areas of their life, maybe other things are going on in their life and that's why they're not happy. But we're really going to focus on salary and job satisfaction, okay? And those two variables. So now what you want to do is go ahead and highlight lines 17 through 21. And you can go ahead and click Run. And what this does is it loads the packages that we need into the current R session. So when you're using packages in R, in every session, you have to load them in by calling the library for them, and this is how you do it. You only have to install the packages ever once, really. But you always have to load the packages in for every R session that you do. So when you do that in the console, you're just going to see what's down here. It's just going to kind of repeat the code that you've run. And then we're going to scroll down a little bit. And we have here a little bit of data. So we have, this is basically just a list, and we're going to call it earnings. We're going to save this list of numbers to a variable. This is a list of salaries in terms of thousands. So we have 120,000, 100,000. This is yearly salaries. And we're going to save this list to this variable called earnings. So you don't really have to highlight the whole row. You can just put your cursor on somewhere on the row like this. You don't have to highlight it, and you can click Run. And when you did that, you should see up in your global environment, you should see this variable earnings has been stored with this list of information, this list of data. The next line, line 30 here, is S rating. That's the satisfaction rating. So that's the percent job satisfaction that the person has. And it's going to be 120 in earnings. That's a person who makes 120,000, and the S rating is their satisfaction rating. So the order matters in terms of all of these numbers. So let's go ahead and run that, and we're going to create this new variable called sRating. And right now we basically have just two separate variables with two different lists of numbers. What we want to do is merge this or stick those together and have it kind of like a little spreadsheet or tabular data set, and we're going to call that a data frame, right? So something that has columns and rows. And that's what line 32 is for, is we're basically calling this data frame function, data.frame, and we're bringing those two lists together. Those lists are also called vectors. So if you want to get into technical terms of what these are called. So we'll go ahead and run that, and we're going to create a data frame called data for model. And you can test whether or not you've done this properly a couple of ways. If you look up at the top right in your global environment, you'll see there's this blue arrow here and this data for model. Well, it's been created. It has 15 observations, which means 15 rows and 2 variables. If you see it to the far right, there's this little square icon here that looks like a little tabular data set. If you click on that, it will bring up a new tab, and it will show you how the data looks as a data frame. So you can just kind of like visually look and see what it looks like. So that looks like it was done correctly. Has anybody had any issues there? Okay. And so now what we're going to do is we're going to create a little graph to look at that data as a scatter plot. And we're going to use a library called ggplot. ggplot is the most popular visualization library for R. So if you're ever going to use R anymore and you need to make charts and graphs, I would recommend using ggplot if you're not trying to make anything interactive. If you're just trying to make like images or static charts and graphs for use in like a presentation, ggplot is really great. So what we're going to do here is we're going to call our ggplot function. We're going to tell it what data we want it to look at, and that's our data for model. We're going to give it an X variable of earnings and a Y variable of sRating. We're going to tell it we want points, which means the geom point. That's basically saying we want this to be a scatter plot. We want you to plot points at those X and Y coordinates. And then the geom smooth, that is a function that's going to give it a linear fit line. So it's going to draw a line through the points using a linear model. So let's go ahead and run that and see what it looks like. And so when you create a plot in R Studio, it's going to pop up on the lower right, and you'll see that it's under the Plots tab. So if it doesn't pop up, click on your Plots tab to see if you have it. And so here we have some data that looks to be, okay, it's kind of artificial data, I'll give you that. But it looks like if there's a positive linear relationship between earnings and satisfaction rating, with a few exceptions with some people. But generally, it does look like it follows this kind of linear pattern. It's always nice to explore your data visually before you get into deeper analysis, right? You just look at it and see what it looks like. So none of that yet is really anything with machine learning. We just got our data in, we graphed it, and now we're going to get into more of what you would do if you wanted to create a machine learning model with this data. So let's scroll down a bit to step 2. Line 38 here is setting our seed. So do you guys ever use seeds in SAS? Have you ever done that yet with SAS, where you have to set a seed variable, set a seed number? What that is you pick a random number. It doesn't matter what it is, but we're getting ready to do an activity that if anybody else wanted to reproduce it in the future, as long as you set your seed as the same number, because we're going to be doing like a random sample of our data. And because it's a random sample, like if they run it in the future and if they don't set their seed, they might get a different sample. So they might get a different outcome. So if you want your project to be reproducible for other people to get the exact same outcome as you, you have to first set a seed. It doesn't matter what number you pick, just a starting point. So we're going to set our seed here of 100. And the next line, line 40, we're going to partition our data. The little bit of data that we have, we're going to divide it into a training set. We're going to use the training set to train our model, and the test set we're going to use later to test how well our model performed. You always want more data to train than you want to test. So what we're going to do in our line 40 here is we're going to ask we're going to ask R to take 60% of the data, take a random 60% of the data, and that's going to be our training set. So then our test is going to be 40%. And we're going to use create data partition, and that's the function that will create that division between training and test. So we can go ahead and run that. Okay, and you can see, again, you can see that it popped up here on the top right. You can click on that little icon to look and see what it looks like, and it just picks random numbers from rows of the data. We haven't actually created the sets yet. We've just created the partition. So in line 42 and line 44, we're creating our training and our test sets. So you can highlight those lines together and then run them. And to see what those look like, you can, again, up in the top right, you can kind of see test versus training, and how test has 4 observations, training has 11. But we can also run some functions in R to take a look at what our data looks like. So in line 46, the head function, if we run that, it will pop up in our console. We'll get to see what the first 6 rows of the training set look like. It's a data frame. And we just get, head is useful if you just want to see a little bit of your data. Then click on 48 and run that code. That's our summary function, and that gives us a statistical summary of whatever data set we want. And we want to look at the statistical summary of our training set, so we put training inside of the summary function. And so you can kind of see what the min and max and of those variables are. That'll be useful later when we have a much bigger data set, like 90,000 rows, which we'll have in a little bit. And then we can run dim to see the dimensions of those two. So we'll run lines 50 and 52 together. We'll just highlight those. And the training set has 11 rows and 2 variables, and the test set has 4 rows and 2 variables. So now in step 3, we'll get to the more fun part of training our linear regression model. So we're going to create a variable for our model. Our model is going to be stored inside of a variable called reg model. And that's just that little kind of left arrow is just our syntax for assigning a value to a variable. You've been seeing that this whole time, but I forgot to mention it earlier. So we're going to use the LM function, that's going to create our model, linear model. We're going to pass it in the Y variable, or this is the response variable, the variable we're trying to predict, because we're trying to predict a person's satisfaction rating. And then we're going to give it this little sort of tilde line, a little wavy line. This is just how you do the syntax of this function. And then we're going to pass it earnings, which is our X variable, or the thing that we're inputting. It's also called the terms variable. And then our data is going to be our training set. So we're using the training set to train the model. So let's go ahead and run that. And all it does is create a variable for the model. But if we then run a summary on that model, we can see some important coefficients. So a linear model is y equals mx plus b. You might have heard that equation, or you might hear y equals ax plus b. So the coefficients are a and b. And that's what we're looking for when we run this function here. And the coefficients are listed in the console. And our b is our intercept. So ax plus b. B is our y-intercept. And we see that it's 34.1054. And then earnings is going to be our a coefficient. And it's positive, so that we do have like a positive. So if we do have a slope, we're going to see this positive slope in our data. And then there's some other statistics that you can use in terms of interpreting your model. And we're going to look at the p-value, which will tell us whether or not there is a statistically significant relationship between these two variables. And if it's below 0.05, then you can say, okay, this is statistically significant. And because it's so low, we can say, okay, there does seem to be a relationship, a correlation between these two variables. Okay, so we passed that test. So if we run line 63, we can get the coefficients. just the coefficients. That was a lot of data that we weren't going to use, so we can just get the coefficients by running our coefficient function. And now we're going to create a function that's our prediction function using those coefficients. All right, so in line 66, we're basically creating our own function that is going to take the A coefficient and the B coefficient. And we've got a formula in line 71. It's going to multiply A by X. The X is our input. It's going to be whatever earnings the person gets, whatever their salary is. We're going to A times X, and then we're going to add B to that. And then it's going to give us a result. And that's going to be our prediction. And we're calling this function predict satisfaction. Caret actually has a predict function that you don't have, so you don't have to do all this work, but I wanted to show you what it actually looks like rather than just give you a one-liner that doesn't really make any sense. So we're creating our own function, and Caret has some like this too. So we're setting B equal to our first coefficient in our model, which is 34 point something, and A is we're setting equal to our second coefficient. So if we change the data set, if we change the data, setting the coefficients this way rather than hard coding the numbers will make it a lot easier if we change out the data to still keep the same code. So we don't have to go back in and change the coefficients if the coefficients happen to change later. So that's just a programming thing. Let's go ahead and highlight this whole section from 66 to 72 and click Run. And all that did was create a function. We haven't fed any information into it. We haven't given it any data yet. And so the next line, we're actually going to feed in the earnings data. And this is just some R syntax here for, we're taking our earnings column. So you see how there's a $sign there inside of the parentheses? It's telling R that we want to use our test data set. And we're passing in our earnings column of data. So we're only going to pass in the earnings variables into that function. And it's going to look at each one, and it's going to run the math on each one of those. And then it's going to save the results to a list called R prediction. So let's go ahead and run 74. Question?
Yes. So all of the different I guess test predictions and then training variables,
yes.
Are these all things that we would do if we had any data set at all? Or is this just specific to this set of data?
This is, if you have any data set. Now, what you're always going to do is create a training and a test set.
Okay.
So if it's images, you're going to do the same thing. You're going to create a test group of images and a training group and a test group. If it's, anything else, you're going to always partition your data into training and test. You might have a different algorithm. Rather, we're using the linear algorithm. You might have a different one, but you're always going to do the same process.
So for the most part, we'd be doing the similar steps and like cleaning out the data. And I will say that what you're not going to do is probably hard code all your data. Like we had a list of numbers. Mm-hmm. You're probably going to bring in a file of data, which we're going to do in the next exercise. So that'll be a little different. All right, so our prediction now, what we want to do is we want to look at all the things that we predicted, and we want to look at beside what the test values were. So let's go ahead. It'll make more sense when we run line 76. So run line 76, and then we're going to open up the little tabular view of our prediction. I don't think hold on. Run. Oh, I haven't done that yet. Okay, so just open up the tabular view of our prediction. And all we see now are our model gave us these predictions. But we don't exactly remember what salaries were passed in. This is the answer, but we don't have a view of what the test data salaries were. To make it easier on ourselves to be able to compare the two values, let's run the next line of code. So we're going to print a data frame of the test satisfaction rating in one column and our predicted satisfaction rating in the other column. So then we can just visually compare the two and see how we did. So click Run, and that's going to pop up in your console. We're just using the print function to print to the console. And so now we'll see, okay, given the test data, given the data that we passed in, which was the earnings data from the training set, given that data, this is what we did. We predicted that the person would be 61% satisfied based on the salary that was the input value. And the actual value, the actual satisfaction rating the person actually had was 75%. So we were a little bit off. In the next case, we predicted the person would be like 65.5% satisfied, and in reality, they were only 60% satisfied. So again, we're a little above what the actual value was. The difference between the predicted values and the actual values are called the residuals. So it's okay to not be exactly correct. It's kind of like we really want to be exactly correct because we want to be perfect. But if we were exactly right for this data, that's called overfitting the model, and it might actually be bad. So just because you get something exactly right for one set of data, if you feed it in new data, it might be totally messed up. So it's okay to be a little bit off, right? You don't want to be, like, it would be bad if we predicted like 100% and the person was 20%. If we were that, or we predicted 100 and the person was 40, that's still a lot. But if we're off by a few, that's probably okay. We're still doing a pretty good job. Does that make sense? All right, so we're visually just testing the accuracy, but we haven't looked at any statistics yet. So let's go and run line 85. And what we're doing now is we're going to use a statistical function called the root mean standard error. And it basically just looks at, like, okay, what's the general standard deviation between these two things? The actual satisfaction rating of the person and our prediction. What's the general standard deviation between those two data sets? And we run, let's just go ahead and run that. Standard deviation is just like how far away were the points. And it's a statistic that tries to tell us, like, overall, how far away were we from the actual numbers. In this case, we get like a 9.78. And what we might want to do, depending on if this was like a real world scenario, we would want more data than we have. Because just like a few rows of data is really not enough for a successful machine learning project. You want a lot more data. Hundreds of thousands of rows would be nice. Even a few thousand rows would be better than just a few rows. And so we want to try to bring that number down a bit more, probably, but it's hard to do that with just a small data set. And we might find that just having satisfaction, just having salary may not be enough. We might have to add in another variable. It may be the case that something else also has some impact on a person's satisfaction rating on the job, like whether or not they like their supervisor, something like that, right? So we might have to tweak the model a bit. But this is the general process for how to do this. Okay. So then if you run the next line, the summary. So this gives us, so when we have the root mean standard error number, then we can rerun the summary of our test data and kind of see, hold on, I didn't highlight all of that. You can rerun the summary and see, okay, well, we can look at how our test data, the range, like our test data went from 60% satisfied to 85% satisfied. Okay, well, kind of a variation of 9 is kind of a lot given the range of our data, which was only like value, it was only like 25 percentage points. So having a standard deviation of 9 might be a little bit high, and we might want to try to bring that number down. Okay, I understand this. Some of this stuff is a little bit, since but if you spend more time with learning statistics and the meaning of that, and you really get into machine learning, which people get their PhDs in, right? People here getting their PhDs in computer science and focusing on machine learning. It really takes that long to really get kind of good at doing stuff like this. You don't have to get your PhD in it to do it. Okay, you can do it with experience. All right. Any questions there? How much time do I have?
Rather 15 frames.
Okay, good. Okay. All right. So our next exercise, we're basically going to do the same steps. So it's going to kind of reinforce what you've already done. We're just going to use a much bigger data set. The data set that we're going to use is in this set of files here. It's going to be called full_dataset.csv. And we're going to use a read_CSV function to pull that in. So a lot of people are like, oh, I like R, but I don't know how to pull data in. But here's how to do it. The read_CSV function is from a package called Reader, and Reader is something that you've installed. There's other ways to read in CSV data and Excel data. And if you're ever interested in that, you can just Google, like, how do you read Excel data into R? There's different packages for it. There's a read Excel package. But it's really the same process of just one line of code will read in the whole data set. So let's go ahead and run line 92. And once you do that, hopefully it's pretty quick. But this is a pretty big data set. It's 107. If you look up here on the right side, and where I'm kind of moving this cursor, 107,005 rows. And there's 9 variables. So I'm going to briefly tell you more about the data set. This is company data. So each of these observations is a company and their market returns. So how well they did in the stock market that year. Just want to make sure I'm kind of how well they did in the stock market. And we have from 1997 to 2016. And we have a few variables. We have the date. There's a couple of like unique keys, the key and the historical ID. We don't really need those 2 columns, but those identify the different companies. We have a market return column. That's the MKTRET. Then we have the dividends to assets ratio. That's the div3_at. Then we have the ranking, the company's ranking based on their dividends to assets ratio. So rank is based on whatever values are in this column, the div3_at column. It goes from 0 to 5. That's it, just 0 to 5, the ranking. Then you have the raw return numbers. And then you have the abnormal return. So the abnormal return is like the company's return. I'm speaking to the choir. You guys know this already, but it's kind of like the difference between what actually happened, versus like what was expected. So whatever the return was, like what actually happened versus what was predicted or expected. And so if it's positive, that means the company did better, right, that year than was expected. And then if it's negative, it did worse. That's kind of a simplified way of saying it, but that's essentially what we're going to look at. So we're going to look at the abnormal return and its relationship to the ranking first off. So that's kind of, those are the 2 variables that we're really going to look at most specifically. And we're going to look at it over time as well. We have 100,000 rows, so we have a lot of data to play with. So let's go back to our script. And we can see if we run 94, we run our head function, we're going to see the first 6 rows of what the data looks like inside of our console. And then we can run our dim function to look at the dimensions of the data. And we'll see it has 107,005 rows and 9 variables. And then if you look at the head summary of the data, you'll see that some of these columns are character columns. So R thinks that they're strings. Well, they're actually numbers, and we want R to see them as numbers. And sometimes when you pull in data, depending on your data set, it depends on like how it was already. If it has any characters in the rows, like this data set had periods for missing data. So R saw those periods and was like, oh, this is a string column. We don't want that. We want to convert it to numbers. So section 99 through 102, let's just highlight that and run it. What we're doing is we're taking those variables in the data set, all of those variables that are listed there, and we're turning them into numbers. So go ahead and run that. And it's going to take those cells that had periods, the missing values, and turn those into NA values. So it's just a little data pre-processing at the beginning that we're doing. And the next thing we want to do is just explore the data with some graphs. So we're going to use ggplot again, and we're going to look at the relationship. We're going to create a scatter plot again. We're going to look at the relationship between rank on the x-axis and abnormal return on the y-axis. And because we have so many values, like so many values that all would be otherwise like plotted over top of each other, we're going to use a jitter function to introduce a little bit of noise into the data so that the points are not all plotted on top of each other. They're kind of just like plotted nearby. So it kind of like gives a little noise to your x variable a little bit. And we're going to set the alpha, which is the transparency of the points, to a little bit more opaque so that you can see through them to see if there's points behind them. There's still going to be a lot of data overlap. But those two, jittering and setting transparency, when you have a lot of data overlapping, they're two like best practices in data visualization to kind of make it so people can see more of the data. I'll show you what would happen if we didn't do that. So let's go ahead and run line 107. It's going to take a minute because it's dealing with a lot of data, and it has to actually remove some of the missing, removes missing data. So it's going to take a moment. We'll rerun it just to make sure. No, mine's not popping up. Is it popping up for everybody else? Yeah. Okay. So mine is being silly. But let me see if I can refresh. So you see, like, if you got it to pop up, you'll see like how many points there are. And as far as like the linear, so this plotted like a line over the chart. And does it look like it has any like positive or negative slope to it? It's pretty much just looks like it's zero, right? It looks like if you were gonna do like a linear model on this, that it's pretty much all the values are right around zero for the most part. But there are a lot of outliers, right? So where are the most outliers in the data, according to your graph? Where are the highest outliers in your data? The ones that are highest above the, what ranking do those values have? Zero, right? So the companies that were ranked 0, oh, here we go, finally, okay. The companies that are ranked 0, some of them have the highest returns, highest abnormal returns, right? Which is interesting, right? And then if we look at these outliers going from 1 up to 5, we see this kind of like situation where the outliers are starting, in every case, there's some that are a little bit higher. So it looks almost like stair steps all the way up. But again, those are the outliers. And we have the majority of values congregated around 0, right? But the 0 ranking, they actually did, some of those companies actually did quite well. And it goes into kind of the math of how the ratios are calculated, right? And so if you guys,
So what do you think of those 0 firms?
Yeah.
Keep in mind, you're classifying these firms based on the firm's dividend yield. How much of dividends are they paying? So do you think the one on the leftmost column, do you think those are the ones which pay low dividends or high dividends? Do you think?
Low dividends.
So those are all the ones which pay 0 dividends. They don't pay dividends, right? And then the second one is the one which is low, then it keeps on increasing to the high. So you can see the two extremes are basically firms which have either no dividend payments, they don't pay dividends, or the ones which are paying a lot of dividends, right? So the good performances are the two extremes.
yeah,
But
so
just visually seeing it is hard to see what
Right.
I just see like 1, 2, 3, 6 blobs of black.
exactly, yeah,
Which is why it's a little bit easier to do stuff with learning rather than just relying on math.
right, exactly. So in the next part 2, step 2, we're going to plot the median values of abnormal return by rank. So the first thing we have to do is create that column in the data set, the median. So we have to do some bioprocessing on the variable abnormal return to get the median by rank, and we're going to run that, and it's going to create that for us. And then we're going to go ahead and plot the rank and then the median abnormal return in line 112. So then we can see, okay, aggregating all that data into just a few values. So what we've done is aggregated all the abnormal returns for all the companies by rank. So we've distilled it into just these 5 values. And we do see this kind of linear relationship here with some interesting things going on with the 0 and the 5. But for the most part, we kind of do see this slope happening. And so that's for all of the years, 97 all the way up to 2016. But what if we looked at it by year? And so section 3 is taking the median by year. We're filtering out all the NA values because we can't do this bioprocessing on NA values. Easier to do it in SAS than R. So we're going to go ahead and filter those out, and we're going to run it. And then we're going to graph that in line 120. And then you're going to get a bunch of graphs by year. To do that, to break things out into subplots, you have to use this facet wrap function in your ggplot function, and we select it on the variable year. So it will give you subplots based on the year. So now we can kind of see the median by rank over time, and we can kind of see the different years and sort of like we see kinds of different relationships here. But again, this is just part of doing more analysis on our data before we get into machine learning. And in the interest of time, we're going to move on to the machine learning part. And what we're going to do is we're going to go back to using all of the data again for this part. We're going to use all of the data except for we're going to filter out the NA values in abnormal return. We have to filter those out, but otherwise we're using still a lot of data. And we're going to try to find, we're going to try to create a model where we're going to predict, here, let me go ahead and run step 3. We're going to predict abnormal return based on giving a company ranking. So the prediction we're going to be doing is predicting a company's abnormal return based on its ranking. So let's go ahead and run line 25 and 26. And that's going to just filter out the NA values for abnormal return. And what you'll see that the effect of that is if you look over here in your top right section, data for model, we have 93,002 rows. So we have fewer rows than we started with, but we still have a lot of rows, which is going to be good for training our model. All right, so we're going to skip down to 132. So we're going to include all the ranks 0 through 5 in our data. And when we skip down to 132, again, we're going to set the seed. And then we're going to create a data partition in line 134. And we're going to, if you see in this line of code, P equals to 0.75, we're going to use 75% of the data to train the model. And 25% of the data we're going to use to test it. So when we create our data partition, then that will allow us to now create our training set and our test set using the same code that we used previously. We just have new data. And I should say not exactly the same code because we have to specify the variables that we want to use, right? So in this case, we're using abnormal return, whereas in the previous exercise, we used satisfaction rating. That was our variable that we were trying to predict on. So in this case, but we're still otherwise doing the same stuff. So we're going to go ahead and create our training and test sets by running those 2 lines. The shortcut for doing this is on a Mac is Command Enter, and on a PC is Control Enter. If you have your cursor in the right place, you don't have to always click the Run button. You can do Command Enter or Control Enter, depending if you have Mac or PC. Okay, so let's go ahead and look at our training set in line 140 and see. Okay, that looks good. We have NA values where there were periods before where there was missing data in the dividends to assets ratio. But abnormal return doesn't have any NAs because we've taken those out. And now let's look at a summary of our training set, statistical summary, and we can see based on all the different variables, the kind of range, the min and the max for each of those. And this is really where we can find outliers in our data. So if you look at abnormal return, you'll see the minimum is negative 1.43 and the maximum is 53.27. So that's a pretty big spread in the data. And then you can go in and say, okay, well, why was that happening and when did that happen? And you can find the kind of when that was going on. But we're not going to do that right now. But this is the process of like looking at the data and saying, oh, are there any problems with these numbers? Like maybe there's a mistake, and then you can go back and change it. But we don't have any problems right now. So now we're going to look at the dimensions of our training and test set in lines 144 and 146. We're going to run those. So just to make sure that we created the data partition properly. So the training set has 69,753 rows, and the test set has 23,249 rows. So that's good. That looks like it did what we wanted it to do. And now we're going to just create our regression model in line 150. We're going to put in our response, or our Y variable is going to be abnormal return. And our ranking variable is going to be our X value that we put in, or also called our terms variable. And then we're going to tell it we want to use the data for model data set. So we can run line 150, and then we can run line 151 to look at a summary of our model, and we can look at the coefficients. And our intercept value, our intercept coefficient is going to be 0.096928. That's really small. And that's where it's crossing the y-axis. And then the ranking variable is negative, so negative 0.01. It's close to 0, but it's negative, right? So you can kind of finish out the rest of the code. It looks like we might be running out of time. Is that the case? You can finish out the rest of the code. It's the same stuff that we did before. And you can kind of see how well the model did. So I'd encourage you to kind of run the rest of it later and just kind of check to see what it looks like with this new data. And you can see, like, ultimately, it's going to kind of look like this. There's going to be a lot of noise in the data. Maybe the case, the linear model might not be the best thing to do for machine learning on this particular data, or we could do some data manipulation to tweak it. But just so you know that, just to kind of get a sense of the process for how you might do it on data like this. Thanks, everybody.
Thank you.
We'll be here. I'll be here if you have questions. Thank you.
So just as an aside, if by chance you're running a dividend growth fund where your objective is basically invest in high dividend yield stocks, that's the kind of analysis you would have done. Okay, to figure out, is that a good investment strategy or not? That's basically what we're doing. All right, thanks, Alice.
Thank you. Thank you.